Bismillah ar-Rahman ar-Rahim. Today we'll talk about chapter 3, which is about the effect of harmonic distortion on power system equipment. Effect of harmonic distortion can be classified into short-term effects and long-term effects. Short-term effects, it can be excessive voltage distortion, more than 10%. It can be voltage flicker due to the interharmonic. Can cause inconvenient tripping of sensitive load, such as relays. It can cause fuse to operate. It can cause resonance, pulsating torque to motor because of the negative sequence harmonic, radio interference. So those are, we call it short-term effect. Long-term increased resistive losses and also voltage stress due to the harmonic. Harmonic current produced by nonlinear loads such as transformer or the electronics device are injected back into the supply system. Okay, for example, over here, this is our system, and over here we have, let us say, the harmonic source over there, and over here we have the load. This is our source. This is the impedance of the source. So this harmonic will be injected back to the source. So this current are interacted adversely with the wide range of power system equipment, most notably capacitors, transformer, motor. As a result, that will cause additional losses on those equipment. This harmonic current can also cause interference with telecommunication system. And also, again, it can cause error in power metering, and some device can be tripped like a relay. The impact on harmonic on the neutral. So the neutral current will be very large, since those zero sequence harmonic will be in phase. Then they will add up over here in the neutral, and that will cause overloaded neutral current. Sometimes it can reach even 300% of the phase current. Not only that, but also it can cause current distortion for large building. Impact of harmonics on the capacitor bank. It can cause the capacitor to fail, and also it can cause the fuse to blown, fuse that are connected with the capacitor. It can cause harmonic voltage, so the harmonic distortion will cause harmonic voltage. So as a result, the current that flow through those semi-capacitor bank will contain also a lot of harmonic, because the current can be calculated by voltage divided by the reactance. If the voltage distortion is within this range from 5 to 10%, that will increase the root mean square current by percenting that range from 10 to 50%. Okay, also those harmonic can cause over voltage stress on dielectric material in the capacitor bank. So as a result, the capacitor will be failed. 10% harmonic voltage for any harmonic above the third will increase the peak voltage by 10%. The problem involving harmonic often show up at the capacitor bank first. The capacitor bank experiences high voltage distortion during resonance. So those harmonic can cause a resonance. So as a result, those resonance will create high voltage and high current. This is the shape of the current that flows through the capacitor bank. which is really large in magnitude and also rich in harmonic. And this is during resonance. The harmonic current shows up distinctly, resulting in a waveform that is essentially the 11th harmonic tiling on the top of the fundamental. So we have roughly the fundamental component, but on the top of that one we have 11th harmonic. So this current waveform indicates that the system is in resonance, and of course the capacitor bank is involved in the resonance. In such a resonance condition, the root mean square current will be higher than the capacitor root mean square current. There is a IEEE standard 92 for shunt capacitor, and those are the specification based on IEEE standard, is that the capacitor should able to handle 135% of the nameplate kilovolt ampere, should handle 110% of rated voltage including harmonic, and the capacitor also should handle 180% of rated root mean square current including fundamental and harmonic, and 120% of peak voltage. Of course this one was in IEEE standard in 92, but now this number is reduced to 135 in the updated standard. Okay, so this is the updated standard. It was updated in 2000, and they reduce that factor to 135. Let us look at this example over here. So we have a capacitor bank. Shunt capacitor is okay. So this is the shunt capacitor. It has Q of 1200 kilovolt ampere. It is connected to a line voltage 13.8 kilovolt. The capacitor is subjected to two harmonics, 5th and 7th. So the capacitor will have 5th harmonic and will have 7th harmonic, and those are given. So the percentage are given. He said calculate the total harmonic distortion for the voltage and for the current. So the total harmonic distortion for the voltage is total harmonic distortion for the voltage will be equal to, we have the 5th square 7th square divided by the fundamental. So we need to find the fundamental component. So fundamental component will be 13.8. 5th is given as 4%. This one given as 3%. Of course, this is from the fundamental component. So 4% of the fundamental, which is 13.8, 0.03 of the fundamental, which is 13.8. Okay. Now for the current, we know that we can find the reactance of the capacitor by dividing the rated voltage square over Q. So that will give us XC. Then we can calculate the current that flow through the capacitor bank, IC. So this is IC fundamental, will be equal to the phase voltage divided by XC. So that will give us the current, the fundamental current. Then we can find the 3rd harmonic, and we can find the 7th harmonic. Of course, we need to modify XC such that it will take care of those different frequencies. And also this is the fundamental current. Also it can be obtained from this formula. This is the phase voltage. This is XC. Can be also obtained like this one. Then you will find V7, and then you will find, of course, the reactance for the seventh harmonic. You need to divide it by 7. For the fifth, you need to divide it by 5, and so on. And then you will find the total harmonic distortion for both. Okay, in part 2, he said evaluate the capacitor duty requirement, which are the maximum peak voltage, root mean square current, kilovolt ampere produce, okay, so we need to find the root mean square current, root mean square voltage, the kilovolt ampere produce, the peak voltage. Of course, for the root mean square voltage, the root mean square, we need to take the fundamental component plus third harmonic plus fifth. Since we have the fifth, right? We have the fifth and the seventh and the seventh. For the root mean square current, we need to do the same thing. Okay, so we need the fundamental component that passes through the capacitor. We need the third, and we need the seventh. Okay, peak voltage, so we need to add the for the peak voltage, we need to add the peak for the fundamental, the peak for the third, and the peak for the for the fifth, and the peak for the seventh. Okay, so those are is already given. So we root mean square, root mean square, KVR. So you see that you pick for the first, the fifth, and so it should be noted that the fifth harmonic current is 20%, and the seventh harmonic current is also around 20% of the fundamental. So they are very close. And then so those this is the table that summarize the result. Okay, so those are the calculated values. Okay, for the peak voltage, root mean square voltage, root mean square current, KVR, which is really below the limit. Okay, so it does not exceed the limit. What are the impact of harmonic on transformer and on machine? Harmonic will cause overheating of transformer and machine because of the two losses, the copper losses or the conductor losses, I square R, that is through the winding, and there is also eddy current losses. Don't forget that we have a core in the transformer and in the motors or in the machine in general. And the eddy current losses will depend on the frequency square. So more harmonic, that means more frequency. So as a result, the eddy current losses also will go up. Well, how to solve the problem of the harmonic in the transformer? Well, one possible solution is to derate the transformer. They recommend 80%, so derating. So that means if your transformer, if you install 100 kilovolt ampere transformer, then that transformer suppose only to work at 80%, at 80 megavolt ampere, and not at 100. So this one we call derating. Also, there is another type of transformer which is called K-factor transformer, and that is initially designed to handle those harmonic. So you can either direct the normal transformer or select a transformer that will handle harmonic, and that is called K-factor transformer, or they call it case transformer. say that the transformer are designed to deliver the required power to the load with minimum losses. Harmonic distortion of the current as well as the voltage will contribute to additional heating. You can design a transformer from the beginning to take care of the harmonic. They call it K-rated transformer. Or you can derate the transformer. Okay, so those are again the how to find the eddy current losses in the transformer by using this formula. So that will provide the eddy current losses. So I square the current that is flowing in the transformer time H square, which is the harmonic, times this factor. Okay, and this is the K factor of the transformer, so it can be calculated from this formula over here. The harmonic current times the harmonic order square over the summation of the harmonic current square. That will give you K. And then the current that is flow through the transformer, the derated current that's flow through the transformer will be given by that K. Okay, so it will depend on the PEC, which is the eddy current losses factor, plus 1 over the K factor times the eddy current losses factor. And those are some typical values for the eddy current losses factor. It depends on whether the transformer is dry or oil filled, and also on the voltage level, and also on the size of the transformer. Okay, this is an example for the K transformer design, K factor. So let's say that the current through a 3 megavolt ampere, the transformer is at reduce the voltage from 11 kV to 690 volt. This is the current, rated current, delta Y. It has Z of 1 plus J 6.2. By using the following table, can the transformer operate in this harmonic? So can the transformer handle those harmonic? Assume that the eddy current losses factor is 15%. Okay, so again you will find the K factor from the harmonic current and from the harmonic order. It is found to be 4, so that is the K factor. Then you will find the derated current using this K factor. It will be 84%. Impact of harmonic on motors. Motor can be significantly impacted by harmonic voltage distortion. Harmonic voltage distortion at the motor terminal is translated into harmonic flux. Harmonic flux do not contribute to the motor, but rotate at frequency different than the rotor frequency. Then as a result it will induce current in the rotor. Okay, so we have in the motor, this is the stator, this is the rotor. We have the normal rotating flux, but due to the harmonic we have another flux that will rotate in another direction. So that flux will induce current in the motor. As a result, there will be more losses. So at those harmonic frequency, motor usually can be represented by rotor reactance connected across the line. And based on IEEE standard 1992 limit, so the limit for the total harmonic distortion will be 5% based on the voltage level, and then the individual harmonic will be limited to 3%. Excessive heating problem begin when the voltage distortion reach 8 to 10 and higher. Such distortion should be corrected for long motor life. Motors appear to be in parallel with the power system impedance with respect to the harmonic current, and generally they will shift the system resonance higher by causing the net inductance to decrease. Okay, so since the motor are represented by inductance and they are connected in parallel with the power system that has also inductance, so as a result the total inductance over here the total inductance will go down, and that will, what will be the effect? The effect will be in the harmonic, because the harmonic given by 1/2 by root LC. So if the inductance go low, harmonic frequency will go up. Impact of those harmonic on the meter that measure the electrical energy consumed kilowatt hour, and also on the meter that measure the power demand. Well, as you know that in Oman, for the big consumer they have to pay for both, for energy and for the demand. But for us as a small consumer, we are only paying the energy, the cost of the energy. So anyhow, those harmonic will affect those energy and demand meter. Those will be affected. As a result, those demand meter will give wrong meter reading. But nowadays, instead of they are using what they call those analog device that based on rotating disc, which utilize single phase induction motor. Nowadays those meter will be digital meter, so as a result the accuracy of the measurement is really high compared with the accuracy of those old analog meter. Okay, also harmonic, it will not only affect motor and the transformer and and as we said that those energy meter and demand meter, but also it can affect the communication cable which is connected on the same pole, since it can induce also a current in this communication cable, then it will cause distortion. Okay, thank you. That's all for unit number or chapter number